Okay, I'm going to try to get through this even faster because I've been taking too long. So please hold on and do your best to keep up. So this in 4.1 we want to talk about what a rare event rule what a rare event rule is for inferential statistics. And remember, inferential means that you've done some kind of study, and from the results you're inferring those results about the entire population. So you only did a small sample, the sample gave you results, those results tell you what the whole group is. So that's an inferential type thing. Now, if the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. So if you have a really small probability, your assumption is probably not correct. Now, an example of that, you have 100 people participate in a gender selection study. As a result, 98 girls were born and only 2 boys were born. What is the most likely outcome of this, okay, or the cause of this? Is it because the selection process failed and this happened by chance, or did the gender selection method really work? Well, the probability of only getting 2 boys, if you think about it, there's a 50-50 chance technically, although there's a slightly higher chance of having a boy, but statistically there's a 50-50 chance of having a boy or a girl. And so out of 100 of them, if you only had 2 boys, that's a very, very small probability, and so therefore it's not likely that that is the occurrence. So we have to throw that assumption out that it's just randomly happened, okay? So what that does mean is that since there were 98 girls, the chances of gender selection actually working is much, much higher, and that's probably what happened. The reason why you had so many girls is because of that selection, okay? Now, on with 4.2, this is talking about basic concepts of probability, and we're really talking about how to interpret probability. So a probability of 0.001 is an event that probably really hardly ever occurs. So remember, probability, relative probability, that event probably hardly ever occurs, okay? And so it's not a very likely event. Now, an event, it's any collection of results or outcomes of a procedure. In other words, guys, when you're doing some kind of study, you're going to have lots of events going on, lots of different things that are happening. And if you're at a park, you're watching a bunch of everything going on at the park. The event of someone coming with their dog to the park, that would be an event. Although that event could break down even further to the type of dog people might be bringing. And so events can be looking at something as a whole, or it could even be breaking it down to its simplest form, okay? So a simple event is when you can no longer break it down into anything further. So if you are looking at Labradors, the event of someone bringing a Labrador to the park, that would be your simplest event because you can't break down a Labrador any further. I guess maybe you could if you broke it down into mixed breeds. I don't know. All right. A sample space are all the possible simple events combined. So in other words, it's all your outcomes, okay? Looking up here at the board, this is going to give us an example of these definitions, so that kind of hopefully helps us understand them a little bit better. So, as simple as it gets, a single birth is just, and you have 1 girl, that's a simple event. You can't break down 1 girl any further than that. Your sample space was, you could have had a boy or a girl. That was your sample space. So if a lady is pregnant with 1 child, she has the chances of having 1 boy or 1 girl, sample space. Now for 3 births, you have 2 boys and 1 girl. That right there is also a single event, 2 boys and 1 girl, but your sample space for all the likelihoods of that occurring. Now this means 3 boys, 2 boys and a girl, a boy, girl, boy, a boy, girl, 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 boy, boy, and so forth. One way to come up with these, this is your sample space, these are all your possible outcomes. One way to do that is through a tree. I could start with my first birth being a boy or a girl. The next child could be a boy or a girl, and from each of those, the next child could be a boy or a girl. And if it's a girl, the next one could be boy or girl, and that could break down into boy or girl. And so if I were to put this all together, this would be boy, 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 girl. And then down here, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. And that's how I found all my possible outcomes, which is my sample space. Okay? Now, relative frequency is an approximation of probability. That is the probability of the number of events A occurring over the number of times the procedure was repeated. Now guys, probability is the same every time. Now we're going to talk about different types of probability, but the way you solve it is always the same. Okay? As far as basic probability goes. So I'm going to get rid of this. It's kind of in the way anyway, and I'll write down the formula for you. I'm going to keep that there because we're going to use it for one example really quickly here. So for relative frequency, the probability of an event, A represents an event, is the number of times of A over the number of times of the procedure. Okay? That's the probability of A with relative frequency. Okay, now, that's when things are not equally likely to occur, that we'd use relative frequency. Flipping a coin, that probability is equally likely, so that's not what we're referring to there. Although, the way we find the probability is pretty much the same. There's the classic approach, which does require you to have equally likely outcomes. This is the flipping the coin type thing. And that is the number of ways that A occurs over the number of different events. It's basically saying the same thing as what that says, okay? There's the subjective probability of A, and that is used when there's a knowledge of the relevant circumstances, or it's an educated guess, basically, okay? Now I'm going to give you an example of each of these, and really you're going to see that it's pretty much the same. There's also the law of large numbers, and this pretty much says that the more often that you do something, the closer your probability is going to be to the actual probability. If you want to try this, I would say go flip a coin 50 times and write down your results. Use tally marks, so you can use frequency, and you will find that the more times you flip that coin, the closer you'll get to 50-50, which is the theoretical probability of that occurring. You have a 50-50 chance of doing heads and tails, so you'd get a 0.5 probability. Okay? Now, let's give an example using the data that we have on the board up here. This is using the classic approach, okay? But looking at this gender probability, we want to find the probability of 3 of the babies being the same gender, okay? So that's the number of times of that occurring over the number of times of the procedure. So here's what we do. The number of times of that occurring is right here in our sample space. To get 3 babies all the same gender, that occurs 1 here and 1 there. Boy, 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 girl, girl, girl. That's the only times that it occurs. So that is 2. That's the number of times it occurs, 2. Now the number of times that we did the procedure, or the number of outcomes, there are 1, 2, 3, 4, 5, 6, 7, 8. So that would be 2 out of 8. In our calculator, to find relative probability, we would divide 2 by 8. In your calculator, you hit 2 divide 8 equals, okay? The answer you get there is 0.25. That is your relative probability. Okay, so the probability of getting all 3 kids the same gender is 25%, or 0.25, as relative probability is always written as a decimal. Okay, so that was one example of the classic approach. I'm going to give you another example of classic, but I'm going to come back to that in a minute. The reason why I use that right now is because I already have this data on the board and I'm going to erase it now. Okay. I don't have a pause on my recorder, that's why you're stuck watching me do everything. Okay, so the probability of an event not being equally likely. A recent survey of 1,010 adults in the US showed 202 of them smoked. It wants us to find the probability, represented by P, of them being a smoker. Probability of someone being a smoker. Okay, so there were 202 smokers. That is our likely event, 202. There were, in the total survey, 1,010 people. Simple. 202 were smokers out of 1010. Now all we do is divide 202 by 1010, and when you solve that, you get 0.2. Done. There's a 0.2 probability that you're going to get a smoker, and that's not equally likely. You don't have half the people in the population smoking, so it's not equally likely. Okay, now I'm going to write up another table here real fast, just for another probability. Try to do this as fast as I can. This is a pre-employment drug screening, okay? So, uses drugs, doesn't use. I'm just doing this as fast as I can. Positive result, negative result. So, for the users, 44 of them got a positive result, and 6 got what we call a false positive, or a false negative, sorry. And then 90 of the don't users, this is a false positive, they got a positive result, and 860 got a true negative, okay? So those are our numbers. Now what we want to do is find the probability of a positive result. So probability of a positive. Well, we need the total number of positives. So that will be 44 and 90. Those are both positive amounts out of the total possible in the study. So we need to add 44, 6, 90, 860, and we get 1,000, just to save us that time. When we add across the top, that gives us 134 out of 1,000. Now you should know by now, divide 134 by 1,000. 134 goes in your calculator first, and then you hit the divide sign, and then 1,000, and the answer you get is 0.134. That is the probability of getting a positive result. Now guys, I can mess with this any way that I want. I would say find the probability of getting a false negative. That would be 6 over 1,000. I could say find the probability of not smoking, or sorry, not using drugs. Well, that would be 90 plus 860 over 1,000. Okay, and so forth. And so you have to consider, what are you looking at? Add everything together that falls within that thing, put it on top, and then the total amount goes on the bottom for your probability. Okay, that was classic right there, okay? That one was classic. The first one was relative. Now subjective. Subjective probability would be example, what's the probability that your next statistics class professor will wear a hat with a huge feather protruding from the top? Okay guys, I don't know about you, but I've never seen that happen before. It's not likely at all, although it could happen, right? And so there is that very, 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 very small chance that it could happen. So I would say there's 1 in 10,000 chance, right? So 1 in 10,000, I would put 1 over 10,000 and get 0.00 what? 0.0001, and that's 1 in 10,000. You could say, oh, it's 1 in a million, so you'd put 1 over a million, and so forth. And so that is the likelihood of that actually happening. It's subjective because you're using your own ideas to come up with what you think the numbers are. And so that's what makes it subjective. Not very accurate, but it does have its place, okay? We use subjective probabilities all the time in our own lives. We think about this stuff all the time. Now technically guys, I would say this has a 0 probability because 0.0001 rounded is really 0 still, but it does have a slight possibility, so that's why we throw the 1 on the end, okay? Alright. Now, another example of subjective probability. What's the probability of you getting stuck in the next elevator? Now guys, this could happen, right? So let's say you have 1 in 10,000 chance again. That would be 0.001, and then therefore, you know, you could use that, whatever it might be, 1 in a million, okay? It's all subjective. Now, carefully consider information. You need to make sure you know what you're looking at and what you need to consider within the information given to you. A study, for example, a study of U.S. paper currency bills with 17 large cities were analyzed for presence of cocaine. Does it matter that there are 17 large cities? No, we're going to look at the numbers, the results. And so, what we're going to do here is take some additional information they're going to give us. So, what they found was 23 of the dollar bills that they studied were not tainted with cocaine, okay? With traces of cocaine. And they found that 211 of them were tainted with traces of cocaine. So, we want to find the probability of it being tainted. Let's make sure I read that right. The probability of it being tainted. Okay, so find probability of it being tainted. We know that there are 211 of them tainted, right? And so 211 goes on top, because that's how many were tainted. Now we need to know the total amount of dollar bills that they use in the study, because that's what goes on the bottom. That's 211 plus 23. That's going to be the total. When adding those together, that is 234. So this becomes 211 over 234. 211 goes in the calculator first. You divide it by 234, and the answer we get is 0.902. Now guys, understanding statistics, I know that's a 90% chance. There's a 90% chance in those 17 large cities that you're going to get a dollar bill or some kind of paper currency that's been tainted with cocaine. It's a lot of cocaine usage. All right. Now, going on. Let's say we want to find the probability of Thanksgiving being on a Wednesday. Well, if you know about Thanksgiving, Thanksgiving is on the 4th Thursday of every November, every year. That means it can't occur on Wednesday, right? We would say that that's a 0 probability. It's not going to happen. So 0 out of whatever bottom number, doesn't even matter. 0 probability. Okay? Now, if you were to find the probability of Thanksgiving occurring on a Thursday, well, that would be 100%, right? There's a 100% chance of that. Now, since we're talking about relative probability here, it's a decimal, we wouldn't put 100%, we would put 1. 1 represents 100%, okay? So, when we're doing relative probability, the numbers have to be somewhere between 0 and 1, because 1 represents 100% of a chance, and 0 represents no chance at all, and so our probabilities are going to be point something, and they're going to all be within 0 and 1, okay? Alright, moving on. Complementary events. A complement of an event, guys, is when is basically the probability of that event not occurring. So if we have the probability of event A, the probability of it not occurring would be its complement. Probability of A, its complement would be the probability of it not happening, represented by A with a line over it in this book, okay? So that's the probability of it not happening. Let's go back to the smokers, okay? The probability for someone being a smoker, let's say, is 0.2. Its complement would be the probability of that not occurring. Okay, so since it was 0.2, that means that there were 808 people. So the probability of that not occurring would be 808. You'll have to look back at those numbers to know where I got that from. 808 over 1010. When you divide 808 by 1010, you get let me find it, 0.8. I knew that answer. I don't know why I was so caught up with my book here. Okay, anyway, so 0.8. Now guys, there's one other way to find a complement. Another way to find a complement is this. You take 1 minus your probability of that event. In other words, it was a 0.2. The probability of the event was 0.2, right? If I want to find out the complement, I would just do 1 minus 0.2, which is 0.8. That's another way of getting that complement, to get that complement, okay? So remember, if you're looking for the complement of an event, you're looking for the likelihood of that event not occurring, okay? All right, now with rounding probability, guys, we're always going to round 3 decimal places. So this is in your book. I'm not rewriting the book. I'm just trying to help explain what the book is teaching you. So when we do this, let's say we have a number 0.90170944017. Okay, since we're doing probability and we're rounding 3 decimal places, this is the 3rd decimal place. The number behind it determines whether or not it rounds up or stays the same. If it's 5 or greater, it rounds up the number. If it's 4 or less, then it keeps it the same. 7 is greater than 5, and so therefore this 1 rounds up to a 2. So this would round to be 902. Okay? Now let's say you get a repeating decimal, 0.3333 repeated. Okay? Well, you're not just going to put 0.3 because you need 3 decimal places. You would just put, we'll do that, and then dot, dot, dot. That's how I'll represent it. Because your calculator will give you this answer, you will just put 0.333, done. Okay? So that's how you would round something like a repeating decimal. Now, if the repeating decimal is big, like 0.7777, then it would be 0.778 because the number behind that last 7 would round that 7 up to an 8. Okay? All right, now interpreting probability. Let me give you a different scale for likelihoods, okay? First off, on a scale, over here is 0, over here is 0.5, and over here is 1, okay? Over here, it's unlikely. In other words, it's not happening at 0. The further you go this way, the more unlikely it becomes. This right here at 0.5, that is equally likely. Okay, that's because it could go either way. It's 50-50. The 1 is what we say likely. If you get a 1, that means that event is going to occur, okay, guys? But this just gives you a scale to determine it. The more you go this way, the more likely it becomes. The more you go to the left, the less likely it becomes, or the more unlikely it becomes. Okay? So let's say you're tossing a coin 1,000 times, and you get a probability, you get your result, now this is your result, is 500 heads. Now guys, we know that 500 is likely what you're going to get because you have a 50-50 chance with tossing a coin. There's 1,000 tosses, 500 is equally likely, so we know that would be a 50-50% chance. But the question is this unlikely? Okay? Oh, sorry, the probability of you getting 500 heads is 0.0252. What I'm saying by that is this, guys. Even though it's likely that you're going to get a 50-50, the probability of getting exactly 500 heads when you flip a coin 1,000 times is 0.0252. It's not very likely, okay, of getting exactly 500. Now, is that probability unlikely? Well, let's look at it. First off, this is unlikely because look how small that number is, 0.02, right? That's not very likely to occur. It's a very small probability, therefore it's unlikely. However, since this is a result that we expect, it is not unusual, okay? It is actually neither unusual or usual. It's neither because you got exactly what you would expect, okay? I'm not sure that example helps out too much or my explanation, so let me try and do another one here. Let's say that you got a result of only 10 heads, okay? Now they're telling us there's a result of exactly 10 heads, but they're not giving us a probability for it. But we can think this through. How likely is it? It's unlikely. It's unlikely to get only 10 heads, especially since you would expect to get a 50-50. Out of 1,000 tosses, you would expect to get somewhere around 500. 10, not very likely. So we would say this is unlikely. Just like the other one was unlikely, but this one's unlikely for a different reason. Now, we can say that without actually knowing the probability. Now, we expect there to be 500, so this is unusually low. So when it's talking about is it usual or unusual, really guys, if you think about the scale I gave you, if it's unlikely on that scale, it's unusual, right? So this is unusual to get only 10. That'd be very unusual. The usual would be somewhere around 500. All right. Now, just to give you some numbers here, or some formulas. If you're a gambler, that's up to you if you want to do that kind of stuff. But the formula for actual odds against something, that would be the probability of the complement over the probability of the actual event. Okay, so those are odds against. Actual odds in favor. That right there would be the inverse of this, or the switch of this, the probability of the event over the probability of its complement. That's how they're figuring odds, okay guys? Odds against something, odds in favor of something. Your payoff odds are going to be your net profit over the amount of your bet. That's going to be your payoff odds. Now guys, if you're a gambler, you probably understand this a little bit better of what you're finding here than I do. But let's just say you bet $5 on the number of 13 in roulette. Oh, sorry, on the number 13 in roulette. You can tell I don't gamble. Your probability of winning is 1 out of 38. Okay? Your probability of winning is 1 out of 38. Because there's 113 out of 38 possible numbers. The payoff odds are given by the casino as 35 to 1. Okay, so let me write this stuff down. This has got to go quick because we need to get through this lesson. Alright, so here we go. It was your probabilities of winning were 1 in 38. And your payoff was 35 to 1, right? Okay, now let's give you a question about this. Find the actual odds against the outcome of 13. Find the actual odds. Okay, so we have 1 in 38 probability, right, for 13. We need to know the probability of not getting 13. Well, that would be 37 out of 38. So the complement would be 37 out of 38. Okay? So now we know the odds for and the odds against it. Okay? Basically, sorry about that. We're going to put these numbers over each other. Since we're trying to find the probability of the actual odds against it, you'll remember that is the complement over the actual. So here we go. 37 over 38 over 1 out of 38. Now guys, when we solve this, we have two fractions on top of each other. Basically what we do is we keep this top fraction the same, 37 over 38, and we're going to multiply it by the reciprocal of the bottom. That means we flip the bottom. This becomes 38 over 1. Now the 38s will cancel, and that leaves us with 37 on top. They become 1s, and 1 on the bottom. So your odds against is 37 to 1. Okay? The next question, how much net profit would you make if you win by betting on 13? How much net profit? Well, because the payoff is 35 to 1, we have a net profit of 35, right? So there's a $35 profit for each $1 that you bet, is what that is. So 35, your net profit, I'm going to this right here. Your net profit was on top. And on the bottom, it was your amount bet. And so what this is saying is, this is 35 over 1. This is a ratio. It can be written as a fraction, first number over the second number. We'll just write it that way, 35 over 1. Basically, this says that you get $35 for every $1 that you bet. Okay? That's your net profit. $35 for every $1 that you bet. All right, so for a $5 bet, how much would you make? If it was a $5 bet, this is how we could solve this. Let me erase some of this junk that's in the way. We'd have 35 to 1. If we get $1 for each one we do, that means we'd multiply by 5 over 5, right? 35 times 5 and 5 times 1, that would give us $175. Technically, I don't need this 5 on the bottom. Let's see, that'd be 25. Let me do this really quick. 25, 15, 16, 17. Yeah, 175. We would just multiply the 35 times 5 because we get 1 for every 5. When I multiplied 1 times 5, that just tells me what to multiply by the top number, which was 5. And so forth, okay? And that's it.